Hey, what's up, YouTube fans? The topic for this video, right, is the reducibility of the human skeletal system, right? Because I've been doing a lot of YouTube videos on the evolutionary reducibility of biological systems, uh, as a counter towards, the argument of irreducible complexity. Um, so, uh, and the human skeleton, it's one of the easiest systems of the human body to demonstrate the reducibility of, because there's so many intermediate forms. But so in any event, first off, because we're Homo sapiens, we have certain distinct features such as orthognathic face, chin. The forehead tends to be more flat rather than sloped generally. Smaller brow ridge generally in Homo sapiens. So some distinct features like that, the chin, right? That's something we only find in Homo sapiens, our species, nothing else. But overall, our skeleton is virtually identical to that of the Neanderthals, virtually though, it's not like that it's completely identical, but yeah, it's overall very much the same, broadly speaking. We know about most of the Neanderthal skeleton because we have a number of very well complete Neanderthal skeletons that have been found, right? They're one of the closest relatives to our species. And then in earlier Homo species, we're the one living member of the Homo group, but then there's also, Homo neanderthalensis, Homo erectus, Homo habilis, Homo floresiensis, etc., etc. I mean, there's a lot. What we see a trend of, right, is larger and larger average brain case size over time, right, in the fossil record, right, for the Homo group, right? And Homo erectus is the first member of the Homo group that we see the bony nasal protrusion, which is still found on the modern human skull. And then we have an earlier group called Australopithecus, right? And then also some other groups that are thought to be other side branches from that group, like Paranthropus, right? And in Australopithecus, we see much the same skeleton as early Homo, but, more tall chimp-like shoulder blades, more facial prognathism, right? Larger canines and incisors. So some primitive features. And then we have an even earlier group called Ardipithecus, right? Which had chimp-like feet. The pelvis was intermediate because it was more so bowl-shaped than a chimpanzee pelvis, but still more stretched out than ours. But it also had big glute attachments, or at least, that's I think if I remember correctly, it has big glute attachments. Regardless on that, other features with Ardipithecus, the foramen magnum is positioned and angled at a spot more like ours than chimpanzees, which is the hole through which the spine meets the skull. The canines are already reduced in size compared to a chimpanzee. And then the earliest group that is thought to most likely be part of our lineage since splitting from our closest living relatives, which are the chimpanzees and bonobos. The earliest member of our lineage is Sahelanthropus tichadensis, and in them we see a large gorilla-like brow ridge, larger canines, but the canines are already significantly reduced compared to other great apes. They likely no longer had the canine honing complex, which is found in most other living anthropoids, aside from human, right? And the foramen magnum, which is the hole through which this spine meets the skull, as I said, it's already changed in Sahelanthropus. So the main early changes in the human lineage are adaptation towards bipedalism, meaning walking on 2 feet, and then also change towards the teeth and jaw, right? Is another distinguishing feature of the human lineage. And then next, the hominid group, right, the great apes, which we are members of, has a large overall body size, far larger than any other living primate, right? So that explains that part of our skeleton. And then great apes, including humans, are part of the larger ape group, and apes have no tail and instead our backbone ends with a coccyx, and we have a dorsally positioned scapula, allowing for highly mobile shoulders, and a unique pattern on the lower molars called the Y5 pattern, where there's 5 cusps divided by a Y shape. Then apes are part of a larger group called catarrhines, and all catarrhines, including humans, have the dental formula 2123, 2123, and downward facing nostrils. Catarrhines are part of a larger group called the anthropoids, and anthropoids have smaller orbits than the tarsiers have, which are the other group of haplorhines. So then anthropoids are part of a larger group called the haplorhines, and haplorhines have a post-orbital plate, right, which is a feature of the skull that we don't find in the other living group of primates, which is the stepsorhines, right? And if you guys want to see, like, be able to visualize what some of these things look like or whatever, you might want to look more into it aside from this video. Unfortunately, I don't have like skeletal models or anything. But in any event, then haplorhines are part of the larger primate group, right? And primates have forward-facing eyes enclosed by bone, which is not something we see in most mammals. So the fact that our skull has forward-facing eyes enclosed by bone, it didn't have to be that way. Most mammal skulls is not like that, right? But the fact that it is because we're primates, and then also because we're primates, we have grasping ability of the hands, right? And most primates have grasping ability of the feet, but that first changed in Australopithecus, right? So Australopithecus first began having feet more like ours, with arches in the feet and the big toe lined with the other toes. And then primates are part of a much larger group of mammals called the therians. And therians have a unique upper nose and jaw with a philtrum. Embryological evidence indicates that the therian, that for the therians, two parts of the upper jaw that previously didn't connect began in our lineage coming together, right? And then part of the upper jaw moved up towards being part of the nose area, right? That's an interesting topic in of itself. And also therians don't have the coracoid bone, right? Which is found in most other vertebrates, if I remember correctly. And then therians are part of the larger mammal group, and there's a lot of remarkable features of the mammalian skeleton. For one thing, almost all mammals, virtually all mammals, have 7 cervical vertebrae, which are the neck vertebrae, and it makes no difference how long or short the neck is. So even a giraffe has 7 vertebrae in its neck, just like me and you, and also something with a shorter neck like a mouse does. There's only 2 living exceptions to this, which are the sloths and the manatees. All the rest of living mammals have exactly 7 cervical vertebrae, whereas it's not like that for other groups of tetrapods such as reptiles, birds, and amphibians, right? And mammals also don't have cervical ribs. And the most common phalangeal formula amongst mammals is 2-3-3-3-3, 2-3-3-3-3. And that one, there's a lot more exceptions, but we are not one of those exceptions. That is our phalangeal formula, right? So telling you the number of phalanges per digit. Mammals are also distinguished by having one lower jawbone, and this is partly because the quadrant and articulate bones, which are found in most other jawed vertebrates in the mammal lineage, they became the malleus and incus bones, which is why another mammal trait is to have 3 inner ear bones, whereas other tetrapods have just 1 inner ear bone, right? And this is something that we have both fossil evidence and embryological evidence indicating that the malleus and incus bones are derived from the articular and quadrate bones respectively, right? I think I'll put a link in the description to that because there's a lot you guys could read about that particular topic of that particular transition. And another mammal trait is that mammals have a secondary palate. And mammals have our teeth specialized into incisors, canines, premolars, and molars. And another change that happens early in the mammal lineage is mammals begin having a single temporal opening on each side of the skull behind the eye, right? And then next, mammals are part of the larger tetrapod group, right? And tetrapods have 4 limbs, right, with digits on the end of each of these limbs. Fossils indicate that the earliest tetrapods commonly had more than 5 toes per foot, right? But then early on, the standard became 5 per foot, right? Which is still the standard most common number amongst tetrapods, typically not more than that for modern tetrapods, right? And by the way, so with how primates evolved arms and hands, right? It's using the same limbs that were evolved in early tetrapods. It's not a fundamental change, right? The bones in your arms and hands are the same as the bones in a dog's front legs and feet, right? Humerus, radius, ulna, carpals, metacarpals, and phalanges, right? It's just adapted towards different purpose in our lineage, right? But it's fundamentally the same, right? And so, the earliest tetrapods from which we descend had 4 legs and feet, no arms and hands, right? But their front legs and feet would eventually give rise to our arms and hands. And early tetrapods also evolved a number of other specializations as they adapted to life on land. The pelvis became better adapted to life on land rather than just having pelvic fins. They began their backbone began having cervical, sacral, and coccygeal vertebrae. The ribs began forming a cage with a sternum. And so the ribs in tetrapods began helping with the respiratory system, whereas in early vertebrates, they only helped with maintaining balance mainly, right? Just as is the case for most living fish. Tetrapods evolved choana, which is a connection allowing for them to breathe through their nostrils. And they lost the skeletal gill arches that are found in fish. Tetrapods evolved amphistylic jaw suspension, which is a matter of how our upper jaw connects to the rest of our skull. And tetrapods evolved the stapes bone of the inner ear, which is most likely derived from the hyomandibular bone of fish. And then tetrapods are part of the larger Sarcopterygian group, which also includes lungfish and coelacanths. Sarcopterygian fish have primitive limbs, which are a few of their fins, right? Their fins have homologs to the tetrapod limbs, right? The tetrapod humerus, radius, and ulna. And unlike most fish, the muscles that move the fins are in the fins for them, whereas for most fish, the muscles are at the base of the fin, right? So this is a precursor to the tetrapods, right? That starts in early Sarcopterygian fish. And then Sarcopterygians are part of a larger group of vertebrates called the Osteichthyes. And Osteichthyes is when we first get bones, right? Whereas all the rest of vertebrates have skeletons entirely made out of cartilage. And Osteichthyes are part of a larger group of vertebrates called the Gnathostomates. And Gnathostomates are mainly distinguished by having jaws and teeth, right? Which are not found in the earliest vertebrates, right? And the jaws and teeth, likely, it's debated, but they likely evolved from modification of some of the skeletal gill arches. Two of the skeletal gill arches of early vertebrates into jaws and teeth, right? Which is supported by developmental evidence because they develop from the pharyngeal arches, right, during embryonic development, just as is the case for the skeletal gill arches. And then in early vertebrates, the skull likely came before the backbone. This is indicated by hagfish, which are the only vertebrates alive that don't actually have a backbone, but they do have a skull, right? And there's two parts of the skull evolved in early vertebrates, the splanchno-cranium and the chondrocranium. And then before there ever was a vertebrate skeleton, there were a number of precursors evolved before that. So early chordates evolved the notochord and postanal tail, right? These were precursors towards the vertebrate skeleton. And they're still found in other chordates, such as the tunicate and cephalochordate. Also, hagfish retains them post-birth, and we still have it, but only during embryonic development. And then chordates are part of a larger group called the deuterostomes, and deuterostomes evolved pharyngeal arches, which were crucial towards the early vertebrate skeleton, since one of the first parts of the vertebrate skeleton to be evolved was the skeletal gill arches. And then in early bilaterians, the early bilaterians see several precursors towards the vertebrate skeleton, such as bilateral symmetry, where the left side mirrors the right side, body segmentation, and the Hox genetic code, right? Which is what allows for, it's a big part of how the positioning of differing body parts gets determined using the different segments of the body, right, in bilaterian creatures, right? And this was crucial towards the vertebrate skeleton. And in early bilaterians, we also get the evolution of the mesoderm germ layer, which in vertebrates develops into our skeleton partially. And in early bilaterians, we get the first brain, which obviously plays a big role in the setup of how our skull is now. And so there you guys have it. That's a basic summary. By no means, this is nowhere remotely close to all that could be covered on the topic. So you guys should research it more for yourselves if you want to learn more. But this is a good starting point. Hope you guys enjoyed the video. See you guys.